Thank you, Julia. And yeah, thanks for the invite to give this talk. I am very happy to be out here on the West Coast giving this talk after hearing about all the snow stories. So I'm kind of nice and warm out here. It's fine. Uh,
Spoiled.
Spoiled indeed, yeah, for sure. So yeah, I originally only had Carl Jung and Eric Friedman on here, but Costas Bakas and Hernando Ambao have been joining in on this work more recently and expanding it out. Um, I should say I'm happy to take sort of questions along the way here if there's any sort of like clarification stuff. Um, and as a sort of like by way of apology, I'm not really going to be going into sort of depth. There's going to be things I kind of skim over and things I don't explain completely, but there's a paper that Julia linked to on arXiv that you can go there and really get the nasty details if you want to. And then you're always welcome to email me to ask me questions. So briefly as an outline, I'm going to give an overview of conventional Bayesian image analysis, assuming that not everybody here is familiar with it. I'll then talk about Fourier space at a very high level to sort of like motivate why we're going to think about the problem over there, and then describe using Bayesian image analysis in Fourier space. I'm going to talk a sort of a few applications of the method, if you like, in terms of approximating Markov random fields, sort of conventional models, taking BIF, I'll use BIFS, Bayesian image analysis in Fourier space. I'll be switching back and forth, but basically working with that data-driven version of it. And finally, I'll talk briefly about our forays into using wavelets instead of Fourier space basis functions. And we have the acronym WIMP for that one, wavelet image restoration using multifractal priors. And that's really all the work of Carl Jung. Okay. So I think you're all familiar with imaging data being on this call, but just to give the perspective of how I'm thinking about the data being laid out, I'm thinking of a 2D or 3D array of pixels, voxels. Actually, everything I talk about will be in 2D, but everything is trivially, I should say, generalizable to 3D. I'm going to think about images displayed as grayscale, so I'm not working with color here. And the grayscale represents intensity, so black will be low, a low intensity, and white will be high. And the image itself is the set of these intensities across the lattice when viewed. Okay. So conventional Bayesian image analysis, a little description of how I perceive it. Others may have a different view, but looking at the image on the left, this is a scan of breast that has tumor in it. This is really, we can actually obtain very high resolutions, but for illustration purposes, I'm imagining a scenario where for this kind of imaging, you can only get the truth with a lot of noise thrown in as well. So this would be what you actually observe, Y being the truth plus noise. And what you really want to do is recover X just from observing Y. Or maybe you want a sort of enhanced X, one where the tumor stands out in particular over and above the rest of the image. And these are sort of games we can play within the Bayesian image analysis formulation, which I'll describe now here below. So in a conventional framework, we have a likelihood indicate a pi of y given x. Pi just indicates any generic distribution. The pi's, all of these pi's here are actually different pi's to each other. They're just representing a distribution in general. It's a common abusive notation in Bayesian image analysis. And the likelihood basically takes you from X to Y. And so it describes the noise degradation process that takes you from the truth to what you actually observe. The prior is, pi of x is I'm being vague here to start with, but hopefully it'll become clearer. What we talk about as known characteristics about x. In practice, in Bayesian image analysis, our priors are inherently incomplete. I can't describe a prior where if I simulate it from it, I'm going to get different pictures of all possible breasts that have been imaged for MRI looking for cancer. It's just not practical. So all I can get into the prior is some kind of sub-characteristics that I know I prefer versus not prefer. So that's as deep as I'll get here, but I'll tell you more about it in subsequent slides. And then we combine the likelihood and the prior in the usual, using the usual Bayesian formulation. So the posterior pi of x given y is proportional to the prior times the likelihood. And having gained the posterior, I want to get a single estimate. And by far the most common estimate in Bayesian image analysis is the maximum a posteriori estimate, the posterior mode. So you have this high dimensional distribution over all possible pixels, and then you go to the very top of that posterior distribution, and the image associated with that point is your map estimate. Okay, so that's a broad overview of Bayesian image analysis in its conventional form. The real key part and the fun part of all this is specifying the priors. And broadly speaking, in development of priors in Bayesian image analysis, there's been two types referred to as low and high level priors. If you look at this image over on the right, you see it's separated into three different regions. I'm using these to kind of indicate low versus high level prior information. So in low level, we're thinking about things like smoothness. So in region 1, I would describe that as being pretty smooth in terms of the intensities across pixels. Edge preservation. So like on the edge of 1 and 2, these edges here are kind of connected. That falls into the low level image category. Feature enhancement and texture analysis. So like region 2 kind of shows that the best. You see that it's kind of like a repeating pattern that has certain sort of texture to it, if you imagine it being like a carpet. So these fall into the sort of low-level priors. High-level tend to be more sort of like geometrical in nature, and then looking at feature and object detection and enhancement. So region 3 here, the shape of it looks something like an ellipsoid. And you can sort of specify into the prior that geometrically, I want to give higher probability to objects with this kind of shape than other kinds of shape. Okay. When we're working in Fourier space, we're mostly working on the low-level priors, but not 100% exclusively, as you'll see in the data-driven example. You can get a little bit higher level. High-level priors, just as one extra bit of note, haven't really gotten all that much use, mainly because computationally they're incredibly painful to implement. Markov chain Monte Carlo doesn't move around the posterior very well. It's kind of hard to specify. It's expensive computation. Okay. By far, the sort of most commonly used kind of prior is the Markov random field prior in Bayesian image analysis. And these go all the way back to the 50s when they were used for agricultural field trials to describe correlations between neighboring plots. It was really Julian Bisag and the Gieman brothers in the 70s and 80s that really pioneered it for image analysis. And it's relatively simple idea that comes as an extension of autoregressive processes in time series. Basically, the idea is that the definition of a Markov random field, Z, which is over the whole array, is a Markov random field if the probability distribution for a particular pixel's value. Let's take this dark blue one in the middle here. Given all of the values in the image, is conditionally only dependent on its 4 nearest neighbors. So if you know the 4 nearest neighbors, then you don't need additional information. The 4 nearest neighbors is for a first order structure. You can go to higher order structures by bringing in the diagonal elements for a second order and so on. So you can make this net neighborhood be bigger and bigger. But the thing to sort of note here is that you get this interdependent correlation structure between neighboring pixels. And computationally, each pixel depends on each other when it's part of the same neighborhood. So you can't put things in a nice sort of conditionally independent way with a hierarchy. You have about as far as you could get from a directed acyclic graph. Basically, this cycles all the way around everywhere. So computationally, it gets kind of tough to deal with. Okay, so that's the motivation for jumping over to Fourier space. Basically, is like to get around this difficulty of specification and computation. So, very quick tutorial on Fourier space for people that are not familiar. When you take an image with grayscale values, we can sort of use Fourier theory to break it down into a set of, as a linear combination of sinusoidal functions. And these sinusoidal functions are sort of specified over Fourier space, or if you use MRI, you might know it as K space. And the 0, 0 frequency here is completely flat. That's basically your mean signal element. If I go over here to 0, 4, I see I have 4 sinusoidal cycles in the vertical direction. At 8, 0, I have 8 cycles in the horizontal direction. And once I move out into off the axes, I now here at this point 8, 4, I have 8 cycles across horizontally and 4 vertically. So you get the idea. You build these up at every single point. And then when you want to create an image, you take your combination of all of these pieces that gives you the image that you wanted. And we can do that pretty easy with Fourier transformation. The key concept here is that we can specify these spatially correlated processes in image space using independent processes in Fourier space. So we're going to take advantage, just on a most simplistic level, look at any of these images and they're spatially correlated images as basis functions. So any linear combination of them is also going to have spatial correlation. And the question is, can we use all these bits of spatial correlation to give us prior information that's useful, even if we only specify them independently? Hopefully that was not too much of a word salad there, but that's basically Fourier space, a whole bunch of independent basis functions, except it's a little bit more complicated. Because at each point in Fourier space, you have, if you think back to your, if you Fourier transform an image, you get a complex data set over in Fourier space. Excuse me. So if you think back to your days of working with complex numbers way back in high school, then you have that you can either specify your complex number as a real and imaginary part, or as a magnitude and phase, or as modulus and argument, depending on what mathematical background you have. So at each point, you have not only the signal itself, but it can be shifted by any argument. So which basically corresponds to a movement wrapping around the torus. Okay. Just another different way of looking at Fourier space, just to sort of try and give a little bit more intuition. We can take this is an image of a snapshot of a little portion of the moon. And we can take that and decompose it into different frequencies. My center of Fourier space is here, 0, 0. So that's zero frequency in all directions. So that's just your overall mean image. Then if I go to some very low frequencies in the X and Y direction, I get a very smooth representation because I'm using slowly moving sinusoids to represent it. Then I go to higher frequencies, I pick up sort of more middle frequency effects. And then even higher, I'm picking up like the small details and noise. Okay. You also might notice a little bit of kind of like ringing effects here. That's part of working with Fourier space. There's things we can do for that, but I'm not going to go into those details. Okay. So how do we specify Bayesian image analysis in Fourier space? Well, it looks pretty similar to what we had before in image space. But your first step is you've got your image, you transform it into Fourier space, and that now becomes the data that you're working with. And we can do that very easily with the wonderful fast Fourier transform algorithm. And then when we're working with BIFS, a posterior is now not just pi of x given y, is pi of the Fourier transform of x given the Fourier transform of y. And that's proportional to the prior in terms of the Fourier transform of x multiplied by the likelihood. So the same, except that we have these script f's in front of everything to represent Fourier transform. And here's a key step, is that now when I'm looking at the Fourier transform of x given the Fourier transform of y, if I'm only looking at one point in Fourier space, because I'm specifying things independently over Fourier space, my Fourier transform at the value kx given the complete Fourier transform of y only depends on the Fourier transform of y at that same k-space point. So my posterior is now a product of a bunch of independent pieces. And it's much easier to work with low dimensional small pieces than it is to work with very high dimensional distributions. That's where all of our gains come in here. So we get a large set of these conditionally independent univariate problems. And for anybody who's familiar with Fourier space filtering, you can think of this as being a probabilistic version of that. In a similar way to how Markov random fields are a probabilistic version of doing kernel smoothing. Okay. So I said earlier that the fun part here is thinking about the prior. So I explained how we set about specifying the priors. I think it's pretty natural, but potentially you could do it other ways. The first step is that we specify the distributional form that we're going to have at each Fourier space location. Remember that we only have a low dimensional problem at each Fourier space location, but we need to specify what form the prior will take there for each of the parameters that are in the prior. And then we need to specify how those parameters are going to vary over Fourier space. So that's why I said conditionally dependent. We're going to set the parameters at each and every point in Fourier space. Now that sounds like it could be a painful process, and it would be if you were trying to do them at each and every point in Fourier space individually. Here I'm looking at step one. I'm specifying, for example, a log normal distribution at this Fourier space point. It has a location parameter and a scale parameter that I need to specify. And so for the location parameter, instead of specifying it each and every location, I take some two-dimensional function to describe how that location parameter is going to vary over Fourier space. I realize I didn't mention, I'm specifying here for the modulus of the signal. So I've got, within Fourier space, I have complex values. This part of the prior is for the modulus, for the magnitude of the signal at each and every Fourier space point. And so basically, if I want more low frequency stuff, smoother realization, I want to put emphasis on smoothness, and I'm going to put more weight in the middle of Fourier space to the magnitude. If I want to emphasize specific frequencies, then I'll put more weight at those frequencies. And I'll show you examples of those. We have to do the same for every parameter in the distribution. If you're working with location and scale, it usually makes sense to make the scale be proportional to the location. Sometimes it even makes sense, well, most of the time, for it to be equal. The prior for the argument is, let's say, messier. Usually you don't have much information about how you want to specify the prior to get the kind of characteristics you want. And I would argue that in most scenarios, just having a uniform prior on the circle is more than adequate for whatever information you have about how the argument should behave. So we just have a uniform prior for the argument at each and every point in Fourier space. So uniform on the circle. Okay. So that's my overview of how we set the prior. Of course, we need the likelihood, and then we need to form posterior estimation. The likelihood describes the noise process in Fourier space. Now, when we talked about the original algorithm for Bayesian image analysis, we were specifying the noise in image space. So here we have to think about it in Fourier space with respect to the modulus and argument of the signal. And if you know what the distribution is in image space, you have to do some careful thinking as to how to represent that in Fourier space. We then specify this likelihood over Fourier space. I should note here, it's actually, if you have spatially correlated noise, it's actually easy to get that into your likelihood here too through a representation in Fourier space, much easier than it is over in image space. We then just combine the prior and likelihood via Bayes theorem. And as I said before, we're looking for a single estimate from the posterior. The map one is the one that sits at the top of the posterior distribution. That's the most commonly sought estimate. Costas Bacchus, who's at KAUST now, is working on extending to be able to work in he's already done a lot of work using Markov chain Monte Carlo at each Fourier space location to be able to create other kinds of posterior estimates like mean, median, percentiles, and so forth. Okay. Probably the most common assumption for noise in Bayesian image analysis that is made, rightly or wrongly, is that it's Gaussian noise in image space for continuous images. That gets a little complicated when you're working in Fourier space because that means that you need a Ricean likelihood for the modulus. And that takes this form here. And unfortunately, there's no sort of neat conjugate prior to work with. It means within this low dimensional problem, you are going to have to do some kind of iterative numeric process to get the estimates. And if we consider the exponential prior, it's actually a pretty simple approach to get to the estimate. If you want to look in the paper for details, that's fine. But basically, we're getting our posterior estimates through some very quick iterative process. The argument of the map is easy, given that we have an uninformative prior and we appeal to symmetry, and basically the map of the argument is just the argument of the data point itself. So you don't learn anything about the argument. All you have is one image. So the argument is the same argument that you saw in the original image. Okay. So I said a lot, and I just want to step back and give a quick sort of overview of the whole thing, of the whole process. So here's sort of toy example. We're starting with observed data Y. Our first step is always just to Fourier transform it, put it in Fourier space to be our raw data that goes into the model. We have an image space noise process. Let's say that's Gaussian. And that will, after Fourier transform over in Fourier space, be Ricean distributed for the modulus. I'm taking a lot of journalistic license in this big picture piece, but it's more just to kind of give you the overview. So the data goes into Bayes' theorem, the likelihood model, and then we also need the prior. So let's say I want something that's smooth in image space. So this is a smooth process in image space. If I want to represent it in Fourier space, I have a lot of mass at the center of Fourier space. That also goes into Bayes' theorem. And then I now build my posterior distribution over in Fourier space. I extract an estimate from there, like the posterior mode. And then all I have to do is inverse Fourier transform it, and I get my posterior estimate of the image. Okay, so let's go through a few sort of simple examples. If I'm using stock images that are often used in computer vision for comparing different algorithms. I'm going to use the exponential prior that I mentioned. So we just have one parameter in the prior now, with a Ricean likelihood for the modulus of the signal. And so my prior and then my parameter function to describe how the parameter of the exponential is going to vary across space is just going to take this simple 1 over the distance of the point from the center of K space to some power D. So basically I have a function that has a peak at the center of Fourier space and then decays away like a kind of inverse cone. And then this kind of works pretty well as a denoising sort of prior. And we can explore the results for different values of D, so different values of sort of acceleration of the decay of the function. This is the true exact. Actually, this comes as a color image in the stock example, but I would just want to work with black and white here, with grayscale here. Adding in a bunch of noise. It was just Gaussian noise. And then looking at different values of D. So the higher D is, the more it trades off smoothness against high level, high frequency information. And depending on what I'm not going to say any one of these reconstructions is the best one in any way. It really depends on your purpose. If you really need to have information about the whiskers in the image, then this would be a really bad option to go for. And so, yeah, it's a trade-off, but you see the way it behaves as you change the value of D. So that's kind of thing you can do with Markov random fields. Here's an example of something well, in theory you could, but you would have to work with neighborhoods that were so big that it would be practically infeasible to specify them. Again, we're using the exponential prior with the Ricean likelihood for the modulus, but we're just going to have a parameter function for the mean of the exponential that is just an indicator function of whether the distance from the origin of Fourier space lies between K1 and K2. So I'm taking a band of frequencies and just saying, I only want to enhance within that region. And we could play around with different sort of sets of K1, K2, and you'll see this kind of looks pretty close to the frequency selection, the hard frequency selection I did earlier. But now we're doing it where we're setting the frequency selected area as being just a prior. So we're using probabilistic frequency selection. And it's doing what it's supposed to. Might not seem particularly useful when you just use this prior on its own, but you're getting the low frequency information here in the when you with low values of K1 and K2, medium when you move it up, and then high frequency is picking up the higher frequency stuff. The cool thing is that the high frequency band does pick up this sort of object out here, which gets lost in the medium, which is good at capturing this object, and the low is good at capturing these sort of two big blob parts. So if you're interested in identifying things within certain frequency ranges, that can be a good prior to use. In practice, you can do better by you can combine parameter functions. I can combine my denoising parameter function along with my frequency selection parameter function and have a kind of mixed prior. And where C1, C2 control how much emphasis you want on the denoising part versus the frequency selection. And so now you get the results down at the bottom. And I think sort of like it more or less speaks for itself what it's doing here. I'm now getting the low resolution, the low frequency emphasis, but I'm also getting some information about the rest of the image too that gets lost in the low, only having the low frequency selection. And similarly for the medium here, I'm now capturing sort of this crevice area, canyon, I guess it would be over on the moon. Here and here in particular, that gets lost in just frequency selection. We actually do better than this if we make our priors for frequency selection not sharp at the edges, but have kind of taper off, and you can do a lot better at reducing this kind of artifactual ringing that occurs there. If you're interested in looking at that, you can look in the paper, you'll see images where it's doing better, and that's the reason. Okay, see where I am for time. What time did you want me to finish up, Julia?
I would say, 10 more minutes, something like that. I mean, it's really up to you. So
okay.
Depends on how many questions you want at the end.
All right. So, I mean, I'm basically going to be skimming through different kinds of applications that are generalizations from here. Overall, I just want to point out, like, what are some the nice properties on here? The big thing is the speed, because we're treating things independently over Fourier space when compared to conventional Bayesian image analysis. The independence means we have non-iterative in general, although you might iterate just within that one Fourier space location. And that means that you have really easy parallelization. We haven't needed to go that far because it's fast, but for really big problems, you would be able to do that trivially. As a consequence of kind of like specifying the priors through parameter functions and a distribution, it makes things very flexible. It's really easy to try different models here for the prior. Whereas if you're working with Markov random fields, to have to re-specify a model with a different neighborhood structure and a different distribution means a whole new set of code. You have to start from scratch. We also get things like resolution invariance, where if you have images on different resolutions, perhaps coming from different scanners, you can still specify the prior exactly the same over Fourier space, at least up to the resolution you're working with. Markov random fields you can't, because if your neighborhood size changes, you have to redefine the whole model again. It's also relatively easy to specify isotropy here. When you're dealing with neighbors in a rectangular lattice, that's kind of pretty difficult to balance the autocorrelation in different directions. Whereas in Fourier space, you just make your parameter functions be only dependent on the distance from the center of Fourier space. Okay. I'm just going to say we can do pretty well at approximating Markov random fields by playing games of matching covariance functions and so on. Just as an illustration here, here's another toy example with the truth of a brain plus noise. And this is a Gaussian Markov random field prior reconstruction using a conjugate gradients algorithm. So this is conventional reconstruction. This is the approximation using BIFS, close Fourier space. It's virtually identical. And we can, like I say, easily try other priors. So here, instead of Gaussian, I'm using Laplacian for the neighborhood structure. And you see, you get, hopefully you can see that the edges are a little more enhanced than what they are over here. But we could make them more enhanced by changing parameter values too. We can do data-driven approaches. So if you have a problem where you have a database of high-quality images, we can easily kind of just learn from those images what the learn a prior for future images from those by, again, just working independently at each location and estimating the distribution at each Fourier space location for each parameter, just by using the histogram, basically. I'm going to skip the simulated example. This is, and just go straight to we actually tried this on an incredibly difficult problem and had, I would say, slight success. So basically, we have the problem is in dementia. Glucose in the brain has been used to help with dementia diagnosis, and to get that measurement, you need to use PET, positron emission tomography, which is expensive, requires a radioactive tracer, and but so every individual is also getting a bunch of MRI, structural, maybe functional, diffusion. So if we could, instead of having to do a PET, use data that we can extract from an MRI scanner, that would be a big saving and a big saving for the patient and so on. And basically the observation is that ASL perfusion is correlated with glucose level in the brain. So kind of a weak relationship, but if we can use the ASL and use prior information from a database of PET images to help better reconstruct the ASL so that clinicians can use it in diagnosis, then that would be an incredibly useful tool. So over on the left, you see an original PET and a corresponding perfusion map. And here's what we play around with different data-driven, use a data-driven BIFS prior that comes from PET to help reconstruct the ASL. And you get this, as you would expect, some kind of like combination between the two. The examples that we've created for clinicians, they say they kind of like them. They actually only look at pretty gross features in the PET image. But what we still have to do, and I don't know when we will get around to it, to be honest, is a kind of large scale validation project with clinicians to show that they are doing as well when they do diagnose, that they blindly that they are doing as well with the data-driven BIFs as they would be with the PET. I don't know. So it's still a little bit of a dream project, I think. Different bit of work. Costas, I mentioned Costas Berkas is extending from using the map estimate to MCMC. So we can get a whole bunch of other kinds of estimates that are not just map estimates. For example, if we were looking longitudinally and you might have two images where a tumor, we want to see if a tumor is changing over time. Then from MCMC samples, you can estimate the posterior mean difference. And you can also come up with probability maps by looking at the output of the Markov chain sample from the posterior. This is still work that, yeah, so it's very much in progress, but of course this is doing pretty nicely with this. There's some nice little tricks that you have to do with the MCMC as well, because you're switching from noise that's specified in image space to what you observe in Fourier space. So making proposal steps is quite fun, but that's a whole different talk. Final sort of other direction is switching to wavelets. This is mainly work that Carl Jung's done. Now, when we're working with Fourier space, we're kind of doing our specification over sort of spatially stationary components that are wrapped on a torus. But by switching to wavelets, we can be quite a bit more flexible in how the prior is specified. It gets more complicated. There's many orthogonal basis representations. People spend their career coming up with these. The simplest, I think, is the Haar wavelet, which is just step function like this. And they go through these various types, like the Mexican hat, the Morley, the Meyer, and up to some really quite complicated ones here, the D4 wavelet. A lot of work goes into these because there's conditions that have to be satisfied in specifying these functions. And people have taken them over to 2 dimensions, which is the kind of thing we've been working with, or at least Carl Jung has been working with. So you can do a lot of things, and I'm not going to try and explain very much about it because probably I can't. I don't have the expertise, but he built these sort of multifractal textural properties into these prior distributions so that you can specify how things behave across different scales. And here's sort of an example of that in practice. He built a sort of an original image here that's made up of different components with different textural characteristics. And also this sort of cloud on the top is deliberate too. You can see then he completely drowns it in Gaussian noise, so that you can't even really see anything. But because he's sort of playing with information at these different levels, you're able to sort of reconstruct out of it. A couple of sort of Bayesian approaches that don't use that textural information and don't use parameter functions are able to sort of pull back some of the information in the data, but he really does a much stronger job when using the prior that has the parameter functions and the scaling process. Okay, so with that, I'm done. But I have very little in the way of conclusions, except for Bayesian image analysis in transform spaces like BIFS, data-driven BIFS, or wavelets. Gives us a powerful different option for Bayesian image analysis. It has a bunch of nice properties, in particular speed and flexibility. And I'm happy that a few people are starting to play around with it. So that's pretty cool. I have a whole bunch of people to thank. I've been working on this for way too long to be at the point where I'm actually, we've just submitted the first main paper, but and I've definitely had a lot of headaches along the way figuring this stuff out, but it's been a lot of fun too. So thanks for listening. So Julia, I guess this is your stop point.